Hello. In this talk, I'd like to give you a flavor of our results on the excitonic insulator phase and its phase diagram in the tantalum, nickel, selenium, sulfur family of candidate compounds. The experimental work has been carried out at Rutgers with samples coming from Technion, and as a theorist, I was responsible for developing the models to interpret the data. So first of all, let me tell you what excitonic insulators are supposed to be. We're all familiar with the concept of exciton, where the attraction between an electron and a hole in an insulator or semiconductor leads to a bound state within the gap, which manifests itself as an intense peak at an excitation energy. However, one can imagine a situation where the gap is sufficiently small or the binding energy is sufficiently large such that the exciton energy is negative and it is profitable to proliferate those excitons, leading to a phase transition. It's even more easy to imagine such a situation as semi-metal, where you have electrons and holes in the ground state to begin with. And in that case, it has been realized that the excitonic order parameter actually corresponds to a hybridization between these two bands, opening a gap by hybridizing them in a way similar to the BCS instability. So theoretically, this state has been proposed back in the 60s, but since then, there has been only a few candidate materials. And on each of these materials, there are just only a few studies suggesting that it might be an excitonic insulator. And one of the issues that one encounters in the studies is that excitonic insulator occurs in actual crystalline lattice, and the electrons and holes are coming from different bands, and they have different symmetry properties. So even if you put an electron in a hole in an S-wave state of relative motion, because the hole, for example, is S-wave and the electron is D-wave, the resulting exciton will break some lattice symmetries. In this case, for example, reflection will take from plus to minus or minus to plus. So excitonic insulator transition will break the lattice symmetries, raising the question, is it actually an excitonic transition? Because the same precise signatures will be provided by a structural transition that can be driven by optical phonons or acoustic modes. That means that's a ferroelastic transition. So the question is, who done it? And the answer that I will try to present to you is that the answer lies in the dynamics. Excitons in the semi-metal are overdamped, optical phonons are supposed to be sharp modes, and ferroelasticity occurs by softening at finite momenta. So the particular candidate material that we have studied, has a second order transition to 128 Kelvin. Below it, an electronic gap develops, and photoemission studies demonstrate a band structure quite similar to what you would expect in an excitonic insulator. Moreover, by using sulfur substitution of selenium, you can enhance the direct band gap in this compound and simultaneously suppress the phase transition, again, consistent with the excitonic insulator scenario, but moreover, implying that there is a quantum phase transition of this phase somewhere in between. The issue, however, with this material is that the order parameter has the symmetry of a quadrupole, and that means that it's dipole inactive, so your IR absorption experiment wouldn't work. What we have done instead is Raman, where there is an incoming and outgoing photon, and by manipulating the polarizations of the two, you can probe dipole forbidden transitions. And in particular, if the polarizations are perpendicular of the outgoing and incoming photon, you're probing these excitations with the symmetry of the soft mode of the order parameter, essentially, or interband transition. If they're parallel, you're probing fully symmetric. And below TC, these two different types of excitations will be mixed, and they will appear in all polarization geometries. So without further ado, let me present you the actual data. So what is presented here is the intensity of the Raman response in color, measured as a function of frequency and temperature. And the features that you observe is that when you go close to the critical temperature, there is a pronounced enhancement of response at low energies. And when you go to even lower temperatures below the critical temperature, you observe the onset of additional features, quite sharp in frequency, corresponding to phonons of the other polarization geometry, as I said in the previous slide. So here's an example. You see this tiny peak appearing. We can quantify that for the whole family of the compounds. And what we see is that the onset temperature of this additional modes decreases with sulfur content. However, even for full sulfur substitution, we still observe this additional modes below around 120 Kelvin. That means that transition at finite temperature is present for all sulfur concentration. So there is no quantum phase transition here. Returning back to other features we observe in the Raman data, there is this blob of intensity of the softening. If we look at the actual spectra taken at particular temperatures, we observe that the softening occurs for this interesting asymmetric-like peak. It's a little bit weird for a phonon to have that shape. And the way to analyze this feature is to use Fano model. So what a Fano model is it's a model where a sharp Lorentzian phonon can interact by this V with a continuum of excitations, presumably coming from some overdamped mode. In our case, well, we can identify this mode. It's actually the excitons in the semi-metal that can decay into unbound particle-hole pairs, suggesting that this excitons should be overdamped. So their dynamics is given just by this damped or overdamped oscillator form, and there are characteristic energies for both of them. And when you look at the actual spectrum, here's the results of the modeling. So the blue line is the excitonic continuum. The green line are the initial phonons. And when you allow the two to interact, you get this red line, which sits right on top of the data. Most importantly, from this fitting, we can extract the intrinsic parameters of phonons and excitons. And here I show them. For the excitonic energy, you see that on cooling to critical temperature, it softens and then hardens. And if I would continue the softening trend, I would obtain a sort of an excitonic transition temperature at 137 Kelvin. What happens for optical phonons is quite different. They actually harden on cooling, and that means that they cannot be the drivers of the transition. However, this coupling V, which I introduced on the previous slide, can boost TC of the excitonic-driven transition. And if we also take into account the acoustic modes that we cannot observe in Raman due to their very low energy, but I'll comment on that in the very end of my talk, you can actually reproduce the critical temperature in this compound. So what we have done is we applied this methodology to all the compounds in the series and constructed this phase diagram. So starting with the selenium compound, where the transition can be very well described as being driven by the excitons and boosted up by essentially inert lattice modes, we found that if you just take this scenario, it predicts that the critical temperature of the transition should go to 0. But at the same time, we observed that the transition is still occurring even for highest sulfur concentrations. And you can see, here's the Raman data for sulfur. You see no softening whatsoever at all temperatures. It's just gapped. And the optical modes, while they do go to lower frequencies, they never go to 0. So the only possible mode that we cannot resolve in this experiment, but we excluded all the other ones that can drive the transition, is the acoustic mode. So we're actually going from a semi-metallic excitonic insulator-like to transition to a ferroelastic driven transition. And if you'd like to ask me whether we observe the excitons inside the gap of this material, we actually do. So here's this intense peak that we observe at 300 millivolts. So this implies actually that the predicted purely excitonic quantum phase transition occurring here is a failed excitonic quantum phase transition, because there is a ferroelastic instability that kind of masks this transition. So with that, I would like to come to my conclusions. I've presented you evidence that there is an excitonic soft mode in tantalum nickel selenium 5. When you dope it with sulfur, we demonstrated that you're going from excitonic to a lattice-driven transition. And we also studied the correlation effects and the coherence of the magnetic body gap opening in the selenium compound There is direct evidence for coupling to acoustic modes at temperatures below TC, and we study in great detail the optical phonon properties. So thank you for your attention, and you're welcome to write me if you have any questions regarding our work. Thank you.